The chi-square goodness of fit test is a powerful tool for assessing normality in your data. In this video, we'll guide you through each step, using Excel's built-in functions to simplify the calculations and visualize the results. To learn more about the chi-square goodness of fit test, check out our previous video on this topic. Let's consider the case study on testing in-app purchase distribution. Many mobile apps claim to be free to play but offer in-app purchases for additional features, content, or virtual goods. Some users suspect that these apps are designed to nudge them towards making purchases, rather than truly being free. The App Fairness Coalition decided to investigate this claim. The AFC collected data from 40 popular, freemium, mobile games, tracking the percentage of users who made at least one in-app purchase within the first month of downloading the app. The AFC hypothesized that the distribution of IAP percentages would follow a normal distribution. They reasoned that most games would have a moderate percentage of paying users, with fewer games at the extremes of very low or very high IAP rates. Use the significance level of 0.05 to test this claim. To perform the hypothesis test in Excel, we will first group the raw IAP percentage data into a reasonable number of categories, then use the mean and standard deviation of the original data to calculate expected frequencies for each group. These observed and expected frequencies will be used to compute the chi-square statistic and corresponding p-value. Finally, we'll interpret the p-value to make a decision about the null hypothesis. Now, open an Excel spreadsheet and write the data values for the percentage of users making in-app purchases. We'll start by calculating the sample mean, standard deviation, minimum, and maximum values. These values will guide us in determining how to group the raw data into categories and calculate the expected frequencies within each group. To calculate the sample mean, use the function average and select the range of the data values. To calculate the standard deviation, use the standard deviation function. And use the minimum and maximum functions to find the smallest and largest values of the dataset. Now, we will group the data values into a reasonable number of categories. To simplify analysis and interpretation of the in-app purchase percentages, ranging from 2% to 45%, we will group the 40 data points into 5 classes, each with a width of 10%, as this grouping is likely to satisfy the common guideline for the chi-square test, which requires an expected frequency of at least 5 in each category, ensuring the validity and reliability of our results. To determine the observed frequency within each class interval, we will use the countif function, which count the number of cells meeting a specific condition. For the first class interval, select the range containing IAP percentage data and apply the condition less than or equal to 9.99%. Now, copy the countif formula used for the first class interval and paste it in the next cell. Modify the criterion to less than or equal to 19.99%. Then, subtract the frequency of the first interval from this result to obtain the frequency specifically for the second interval that is between 10% and 19.99%. Similarly, paste the formula to the remaining cells, adjust the criterion for each subsequent class interval. Next, we'll use Excel's norm.dist function to calculate the expected proportion of data values within each class interval, assuming a normal distribution. For the first class interval, input 9.99% as the x value, select the previously calculated mean and standard deviation, and set the cumulative argument to true. Next, fill the remaining cells by copying and pasting the formula. For each subsequent interval, simply update the x value in the norm.dist function to the upper limit of that interval and subtract the cumulative proportion of the previous interval to obtain the proportion specific to that class. To ensure the total expected proportion sums to 1, we will treat the first and last class intervals as open-ended. This means the first interval represents less than 9.99% and the last interval represents greater than 40%. This accounts for the entire range of potential values in the normal distribution. For the last class interval, 40% or more, subtract the cumulative proportion of values less than or equal to 39.99% from 1. This accounts for all values above 39.99% falling within this final, open-ended interval. To calculate the expected frequency for each interval, multiply the total sample size by the corresponding expected proportion calculated in the previous step. Now, for each category, calculate the squared difference between the observed and expected frequencies, and divide this value by the expected frequency. The chi-square test statistic is then calculated by summing these individual values across all categories. Under the null hypothesis, the chi-square statistic follows a chi-square distribution with k-1 degrees of freedom where k is the number of categories of the outcome variable. To find the p-value, use the function chi-square.dist.rt and input the calculated chi-square statistic and the degrees of freedom as arguments. The p-value is 0.5788. Based on the results of the chi-square goodness of fit test, where the p-value exceeded the significance level of 0.05, we failed to reject the null hypothesis. This suggests that there is not enough statistical evidence to conclude that the distribution of in-app purchase percentages across the 40 freemium mobile games significantly deviates from a normal distribution. The comparison of the two distributions can be visualized using a side-by-side clustered column chart displaying both observed and expected frequencies.